What is proportionality? And talking about how that ties in with graphs and linear equations. Some linear equations are not proportional, and some linear equations are. So, just to talk about proportions, like what the heck does that even mean? So, if, say, one tire costs $100, okay? You'd be able to make a prediction based on how much two tires would cost, three tires cost, four tires cost, and this is a proportional relationship. It's growing by the same amount every single time you buy a new tire. Now, if there were a $30 installation fee, that would throw off proportionality. So if there were this would be your y-intercept, the plus 30. That would make it not cross through the origin. Anytime that a line is crossing through the origin or 0, 0, you have a proportional relationship. Anytime that it's not, you have a not proportional relationship because this plus 30 will throw everything off. If you buy one tire for $100 with a $30 installation fee, you would no longer be able to make the extrapolation or prediction on how many tires you could buy would cost X amount. There's always going to be that plus 30 that's throwing it off. So this is also where direct variation comes in because one thing directly affects another. And if you have like a hidden fee in there, like a plus 30, that's going to throw off proportionality, which in essence will also throw off direct variation. Direct variation is another way to talk about a proportional line. And I'm going to show you some examples of that. So another thing that is coming up is Pythagorean theorem, and that's the reason is because whenever you're using direct variation, you're using linear equations. The rise over the run forms right triangles, and those right triangles, the side you'd be looking for is the hypotenuse, which is the longest side, or which is opposite of the right angle. So the thing that you're going to be involved is going to be highly involved with the Pythagorean theorem is balancing equations, solving for a variable, using inverse operations, and using rise over run. That's why we emphasized linear equations so much, because these things, you have to be able to do that before you can do these. Okay, so here's an example of a problem. Dylan makes 336 for 32 hours of work, and I'm going to set up a proportion just to show you. So if we know that Dylan is making $336 for 32 hours of work, I could figure out how much he makes in 1 hour by setting up a proportion. So what this is doing is creating equivalent fractions with a missing piece. Creating equivalent fractions with a missing piece is solving a proportion. Very, very simple. You do that by using cross products. 32 times a mystery would be 32 times your variable. And this is where solving one-step equations comes in. Equals 336. Okay, so we would do 336 divided by 32, and you'd get Dylan makes $10.50 an hour. Now you can use this unit rate. 1 hour is $10.50. You can use that to make estimations and make extrapolations based on that. So like you could figure out 50 hours, 500 hours, how many hours would you have to work to get X amount of money. Another thing that comes up is whenever you're writing an equation, and we spent a lot of time writing equations and trying to figure out if whenever we make the y equals kx or y equals mx, is anything being added or subtracted after that? And that's whenever we would go the change in y, which is 75 to 120 is 45. And that increased by 1 on your x, so that would be 45 over 1. Okay? Now, here's where you can figure out if a relationship is proportional or not. You find the slope first, which is your change in y over your change in x. So far, we have 45 over 1. Okay? You can see here that this says 75 and our slope is 45. That would mean that something is being added. So if we did 45 times x, which is our number of hours, we get 45 times 1. That would give us 45. And then I would always ask the question, how much would you have to add or subtract to get to 75? And you say plus 30. So this is where we have 45x plus 30. This is a not proportional relationship. The same thing's happening here. You do the same process. It's increasing by 45 and it's increasing by 1. So we have 45 over 1 again. Then we plug it in. 45 times 1 is 45. We now have a proportional relationship. What this problem is asking you for, the ratio, is saying your y over your x. So 45 over 1. And then you're going to see equivalent ratios come up. 90 over 2. And you can see it's going to be counting. 135 over 3. And every time you divide these, it's always going to equal 45. This is what makes a proportional relationship. Nothing's being added or subtracted. If you spent 0 hours working, you would make 0 money. Here's an example and a non-example of what a graph would look like for proportional and non-proportional. You can see here that the y-intercept is at 30, and you can see here there is no y-intercept crossing through the origin. This is the simple differentiation between proportional and not proportional. Not proportional because it's not crossing through the origin. Proportional because it's crossing through the origin. Okay? So far we've looked at a word problem to discuss proportionality. We've looked at a table to determine if something is proportional, if it's growing by the same amount, direct variation. And then we also looked at an example and a non-example of an actual graph. If it's crossing through the origin, check. If it's not proportional, there is no direct variation. So what about this Pythagorean theorem thing? So there is a formula, a squared plus b squared equals c squared. Anytime that you have a quadrilateral and you cut it in half, you're looking at two right triangles. The sides that are adjacent to each other are going to be your A and your B, and there's your right angle. Your right angle will always point at your hypotenuse, which is C. So A and B are called legs, and C is called the hypotenuse. Just some facts to throw out. If you have a squared plus b squared and it equals c squared, you can create that same exact triangle as a reflection image, and then that will create a symmetrical quadrilateral with using two congruent right triangles. This is how they used to do measurements back in the olden days with like string. They would use the same length of string and then make a quadrilateral that was completely even on all sides, making squares or rectangles. So whenever you're given two pieces of information, this is where the balancing equation comes in. Let's say let's say you have a leg that's 3. I want to get rid of some of this stuff. All right, let's start abstract. A equals 3, B equals 4, and C equals, I have no idea. Okay, so we plug it into the formula. 3 squared plus 4 squared equals C squared. Order of operations says, do you see any parentheses? The answer is no. Do you see any exponents? The answer is yes. Solve one at a time. 3 times itself is 9 plus 4 squared equals C squared. Do you see any exponents? Yes, I do. Drop it down. It's 16 equals C squared. So 9 plus 16 will give you 25 equals C squared. And this is where the inverse operations come in, just like addition, inverse operation is subtraction, just like multiplication, inverse operation is division, and vice versa. Whenever you have a square, the inverse operation of a square is a square root. So taking the square root of C squared will give you C, because C times C is C squared. So that means what you do to one side of the equation, you have to do to the other. The square root of 25 is 5. I use the example of a 3, 4, 5 triangle, the legs being 3 and 4, and C, the hypotenuse, being 5, because this is called the golden ratio. There are certain numbers you can use for the legs that will always equal whole numbers. 3, 4, 5 is one of them, so that's a shortcut. If you see a 3, 4 triangle or a 3, 5 or a 4, 5, you know that the other one is going to be a 3. It has to. But what if you're given another piece of information, not just A and B? This is where balancing equation comes in on another level, but nothing impossible. So let's say that you're given a leg. 3, you're not given a leg, and you're given the hypotenuse. Then you plug in the information. 3 squared plus b squared equals 5 squared. Follow your order of operations. 9 squared plus b squared equals 25, or get rid of the squared. Then you have to isolate the variable, get b by itself. So how can you get rid of a positive 9? You subtract a 9. Balancing an equation. That goes to your 0 pair. You're left with b squared equals 16. Then we're right back to where we started and finding the square root of both sides. Square root of b squared is b, and square root of 16 is 4. So b equals 4. And the reason I wanted to use 3, 4, 5 again is because the math works out nicely. Whenever you're going to get a decimal, which some of the time you are, just make sure you're going out to the hundredth place, like 4.28. This is the basic idea of finding the legs and or hypotenuse of a right triangle.